The title of my talk today is Improving Checkpoint Restart with Lossy Compression, And this work is done in collaboration with my advisors, Luke Olson and Mark Sneer, as well as Frank Capello from Argonne National Labs. So Checkpoint Restart has become fundamental to a lot of long-running HPC applications. It gives you a lot of benefits. One, should your application crash, you're able to recover from this failure. It also allows you to extend the execution of your job beyond a single time allocation. So now you can, instead of running for a few hours, you can run for days, weeks, maybe even months if your application requires it. It also allows you to do a few other things, such as visualization or selectively diverge your simulation to do some parameter testing. But fundamentally, Checkpoint Restart is not required for your application. It's stuff added, it's runtime added to the application to give you benefits such as those listed here. So efficient Checkpoint Restart allows applications to become efficient, to be scalable. And no one likes inefficient checkpoints. However, we need checkpoints to be permanent. They need to be saved to some permanent storage. The best example of this would be the parallel file system. But we have a data movement problem. As you can see in this sort of rather old figure at this point, this orange trend here is the performance bandwidth of writing to the parallel file system. The peak was 10 gigabytes per second at this point in time. And as you can see, a relatively small number of nodes has saturated the bandwidth. As we see, we start flattening out here. And on a machine like Blue Waters, the bandwidth of the parallel file system is a terabyte per second, or a little bit above that. You can still get this sort of flattening out of the curve if you use enough nodes on Blue Waters to saturate bandwidth. And so you may say, well, let's use faster memory technologies. Let's use SSDs, let's use RAM, and sort of to improve our memory performance to get around this whole bandwidth issue. But there's another dimension to this, and that is power consumption. Today's HPC systems are already consuming megawatts of powers, and the top power consumption system is double-digit megawatts of power. And so this image here is taken from a talk at a computer architecture conference that shows sort of this power issue sort of magnified. So this is done in 40 nanometer CMOS. What I want to show you is the difference in power consumption required to do computation opposed to data movement. So if we take floating point numbers and we do a fuse multiply add, A times B plus C, the energy required to do that is on the order of, here it says 50 picojoules. If we need to go and do a read or a write to, let's say, SRAM, which would be like cache, or even DRAM, the energy required to do such an operation is considerably more. Here, for a DRAM operation, it's 3 orders of magnitude more. We know that it's going to take time, but it's also consuming drastically more energy. And future HPC systems, they're going to be power constrained. So we might not be able to run all the computer at peak performance. So computation is cheap. Data movement is the issue. It's already becoming an issue for bandwidth reasons, but in the future, we can expect it to be limiting on power consumption when we are operating in a constrained environment. So what are some solutions to solving this data movement problem? Well, if it's expensive to move data in terms of time and energy, why not let's recompute it? Computation, as I showed there, was cheap and power-wise. It's very fast compared to accessing memory. So for some parts of your data, that may be useful. And it's an operation that people do instead of transmitting data from one node to the next. They'll just recompute it. Another option is, well, let's leverage the complex memory hierarchy that's in current systems. And as we get non-volatile memory on nodes and next generation systems that are coming online, we can efficiently write, in this case, we have 2 Checkpoint Restart libraries, SCR and FTI, that make use of the memory hierarchy. So it'll first write checkpoints to main memory, and then SSDs, and then my neighbor's main memory, and their SSDs, and slowly filter it out to the parallel file system to allow the application to proceed with what it's meant to do, and that is to do science, to do its computation. Another approach here is we can reduce the volume of data that needs to be transmitted by applying compression techniques like gzip or something. But combining these solutions, these are known solutions, and they are been shown to work and work effectively. Combining these solutions offers new avenue to combat this problem, not only the limitations of bandwidth, but also the limitations of power consumption going forward. What I would like to talk about in this presentation is how can we use compression. And when you talk about compression, there's two types of compression. We have lossless compression, such as the gzip program, and then we also have lossy compression, sort of our JPEG. So the hallmark of lossless compression is there's no data loss. When I decompress it, I have the same data every single time. With lossy compression, that's not always the case. There's going to be some error. But the nice thing is you control that error. You get to specify what is acceptable in your application. If we think in the context of HPC floating point data sets, they're very, very difficult to compress with large compression factors with lossless compression. And that's just due to how random floating point data is, its representation, how it's spatially represented. Comparatively, lossy compression can give you higher compression factors. If you want high compression factors for lossless compression, you have to spend a lot of time to lower the entropy of your data set in order to achieve that. However, with lossy compression, if you want it to compress fast, just allow it to add in more error. The more error you add in, the faster it becomes. So if we think about where these two classifications of compression algorithms are being integrated into current systems, there have been several recent publications in the hardware community about how to implement lossless compression inside the memory hierarchy, transferring data from main memory to RAM, from disk, in this case it would be like a SSD on a node, to main memory, and how to do it efficiently with lossless compression. If we think about lossy compression, there's been some research looking at how can you use it for checkpoint restart. And a lot of this research here is sort of in trial and error. Let's compress with this amount of error. Do we get the same result? Well, how do you know that you get the same result? It requires a lot of domain-specific knowledge. You need to have a test case and know exactly what you're looking for to sort of verify the accuracy. But I would like to sort of get away from needing that really deep domain-specific knowledge by looking at first the fact that, well, a large class of HPC applications are solving some PD, some ODE, but they're not solving them exactly. It's too prohibitive to solve them exactly, so we approximate the solution to them. So if we approximate solution, we know there's already going to be error in it. So lossy compression is starting to make a little bit more sense here in the fact that, well, it has error, our approximations have error, so let's investigate how we can use lossy compression to accelerate HPC checkpoint restart. So the key of using lossy compression is this error tolerance. How much error do I add in? Well, what is really meant by this error? Is it the number of bits I want preserved in my floating point number? So I can go from 64-bit down to 32-bit, go from a double precision to a single precision. Well, I've saved half as much memory there. Maybe I would like the error to be bounded, either an absolute bound or relative bound for every data point in my domain, every element of my vector. And then so with that, you can assign some tolerance, 1e minus 5, 1e minus 1. But what do these tolerances mean for your application? Some will give great compression ratios. If you compress 1e minus 1, well, that's going to give a lot of error, but it's also going to give a very good compression ratio. Compress to something like the accuracy of double precision, then you're going to get very small, but you know that your answer is going to be accurate. So understanding the impact of this error tolerance on your application is critical for effectively using this, for effectively being able to restart the simulation from a lossy checkpoint. So as I mentioned before, HPC applications are approximating the solutions to ODEs or PDEs. So let's think of the error that's added in from lossy compression as if it was numerical error that we've already thought about when we went and discretized the domain, applied numerical methods, and started solving this problem. So the accuracy of your simulation depends on a couple of things. It depends upon whatever numerical method you are using to solve the problem. That numerical method has a certain order of accuracy. It could be first order, second order, third order, whatever it is, it has a guaranteed order of accuracy. And that order of accuracy is specified based upon the discretization of the problem. We discretize the problem at a resolution that we feel is sufficient to solve the problem that we are needing. So if we know the order of the method, we know our discretization, we know how accurate our solution is, how accurate we are asking for a solution. So in this example, if we say that we have a 1D PD we're solving, we'll say we're solving it with Runge-Kutta method of order 4, and we have our discretization of 0.01. We know that our solution, U of H, or numerical solution, is accurate to 1e minus 4. So what that means is any solution, UH tilde, any numerical solution that's been perturbed, so we have our original numerical solution plus some error. If it is less than 1e minus 4, the numerical solution and this perturbed numerical solution are identical according to the accuracy that you specified. So there's no difference in them. However, if the error is greater than 1e minus 4, we can relate that back to some related method. In this case, if we say that the accuracy is 1e minus 2, well, that's the same as saying I have a solution that's accurate to the order of Runge-Kutta version 2. So the way that we can apply this selection methodology to select this compression error is we have an offline component and then the online component. The offline component takes simulation parameters, the stuff that you think about when you're specifying the config files, when you're before you actually go and run the application. You have what numerical method you're calling in your application. You have your discretizations. And based upon your numerical methods, you know the order of accuracy, you have your discretizations, you can find out the exact accuracy, get a number, and then you can assign these compression error tolerances based upon your accuracies to whatever numerical methods that you're using or are related to the problem. And that can guide the selection of your lossy compression tolerances. Like in this case, anything, if we are using RK4, let's select it as 1e minus 4, so we're at the level of accuracy for this problem. And that's where we transition from the offline to the online. So now we're actually running the application. We're running the application, we're updating our solutions here. We have RK4 updating 3 variables, U, V, and P. And periodically you're going to take a checkpoint, and in this case it's going to be a lossy checkpoint. We're going to have our compression error tolerance 1e minus 4, and we're going to checkpoint our state variables U, V, and P. And then we're going to start computing. We're going to update our state variables again. We're not updating the compressed versions of our state variables. We're still updating the original uncompressed versions. Only when we have to restart, be it application crash, or we need to extend beyond a time allocation, will we go and start computing on the approximate versions, the one from decompression from a lossy checkpoint. Those will have some error associated with them. But is this error bad? Can we still get an accurate solution, accurate up to the tolerance that we specified with this? So before we go into some actual HPC applications, let's look at this in the context of 2 sort of test model problems. We're going to look at a 1D heat equation, which is heat transfer in a 1D rod. We're going to have the left and right endpoints fixed at a constant temperature, and we're also going to have a point source in the middle, heating the middle of the rod. We also have a 1D advection equation, which is simply a sine wave propagating, in this case, to the right. We're going to apply periodic boundary conditions, so what falls off the right end of the graph pops it on the left. And we'll see how the error that's added in from a restart from a lossy compressed checkpoint affects the solution. Our lossy compressor in this case is SC, which is a compressor developed or in development at Argonne National Labs. Our compression error is always going to be less than the tolerance dictated by the numerical method and the discretization of the domain. We'll use relative and absolute errors to enforce this. And what we're trying to verify is the accuracy of the problem is always going to be greater than the error that we add in from compression. Is no matter how far you evolve time, this should always hold. We're never going to add an error that's seen by the mathematics. It's always going to be mathematically insignificant error. So this is the error that's added in from the 1D heat problem. So on the x-axis, we see the domain of the rod from 0 to 1. And then on the y-axis, we see simulation time. So each rectangular box here is the error associated at that grid point in the rod. We take 2 checkpoints, one at time 0.6, one at time 1.1. So we can see when we restart at time 0.6, there's error in the solution. And over time, as we evolve, the error is removed. The reason this error is removed is the problem itself is converging to a time-independent solution. It's converging to a fixed value. And even when we restart the simulation again from another lossy compressed checkpoint, that error is also removed. So let's look at how this error relates to the accuracy of the simulation. So if you go and compute it, the accuracy is 1e minus 5 in this case. And we see that our selection of an error tolerance is less than that. We have no error in the solution before we restart. Only when we restart do we add in error. And we initially add in error, it becomes removed. We restart again, we add in more error, but it's removed. It's a diffusive process. You're spreading the error out, and you're also, in this case, converging to a fixed solution. So you have the nice removal of error. Let's contrast this with the solution to an evection equation. And here we have the sine wave that's propagating to the right. We see that there's no error before we take checkpoints at these times. And then as you continue to take checkpoints, the error accumulates as the line's getting darker. And also, they're going diagonally to the right. Recall that the sine wave is propagating to the right. So error is being propagated in the domain. If we look at the inf norm of this, we see error is remaining in the simulation and is accumulating as the number of restarts increase, and it's remaining in the domain. It's not being removed. The periodic boundary conditions don't allow it to be removed. So to summarize, just looking at these 1D problems, is we can compress below the level of accuracy and not affect the simulation. We still get the same result. PD properties such as diffusion, spreading out error, periodic boundary conditions, and sort of an evection type problem maintains error. So we can increase our knowledge about selection tolerances based upon PD properties, selection of boundary conditions. So let's look at two HPC applications that have been run on Blue Waters, PlascomCM, which is a multi-physics code developed at the University of Illinois. In this case, we're solving a 2D Navier-Stokes problem. It's a simple flow past a fixed rigid object. The flow will break around it and eventually exit the domain. This Nek5000 example is a 2D simulation of passive heat transfer in a rod. It's a periodic simulation. Flow is passing over a rod, cooling it, and what comes out one end pops back in through the other. So we sort of got that evection type problem I mentioned before. If we look at compression factor, this is for the Plascom, the plasma physics code. We see it's highly related to how much error you want to add in. If 1e minus 1 is good for your tolerance, well, you can get a compression factor of 100x. The data is 100 times smaller than what it started off with. For our simulation, it was 3.25x. It's the factor of reduction that we have. If we look at the error, a similar story. We restart. At every restart, there is a spike in error. As time evolves, the error is dissipated, and we see some accumulation of error with every subsequent checkpoint, and this is in all the state variables from the checkpoint. So if this plays, we can look at the right-hand side. This is the simulation itself. This is the momentum variable, and I apologize for the frame rate. It was much faster on my laptop. And the right is the error in the solution. So at each checkpoint and at every 250 time units, there is a restart. You can see there's a large spike in error, but it eventually, like there's a spike in error, it spreads to the domain, but gradually it starts moving to the right in the direction of flow. And if you look at where error starts to accumulate, if you look in the regions where there is zero momentum, so the flow is not moving, particularly right in front of the rod, there's accumulation of error. So not only is it the properties of the PDE, the boundary conditions, it's also a function of your geometry of the problem that you should also factor in. All right, so our next application is Nek5000, this heat transfer problem. And we have three variables that are being written in the checkpoint file. We see drastically different compression factors for these. Relatively same between momentum and pressure. Temperature is drastically smaller. The reason for this is an artifact of the compressor. The temperature variables are much larger in magnitude, and they differ quite frequently in position and its nearest neighbor, going from positive to negative. And it's really hard to curve fit that information within a specified tolerance here, 1e minus 6. So you get lots of data that you cannot predict with a linear quadratic interpolation, and so you have to do some other compression mechanisms, so we don't get quite as good of a compression factor. Here we're just looking at the temperature solution, and you can see something very similar as the other graphs. We are always less than the accuracy of the mathematics, and we restart a checkpoint. In this case, we have some reduction of error, and every checkpoint we have removal. And in this case, we're solving for temperature. It's a convection diffusion problem. We can see the diffusion is error is being removed. And I said we had the periodic boundary condition, so flow is flowing back in, and you can see sort of the attenuation of error. So if we'll look at this, you'll notice that this figure here is a lot more grainy. That's not because of the frame rate of this laptop. That's due to processor boundaries. Like I said, the variables themselves change quite drastically, going from 600 to minus 300. And you get very distant values for little parts of the domain that are assigned to processors, so you get sort of this blocky pattern here. All right, so conclusions is simulations can effectively be restarted. They can be restarted from this lossy state. And they can be restarted and not add error as long as you select a compression tolerance at less than the accuracy that you've requested mathematically. With that, you are giving the same simulation that is indistinguishable, but there's a few things that we can add in to improve this that I haven't quite looked at, is PD properties. Diffusion can move error around. Periodic boundary conditions does not allow error to be removed very easily, if at all, and error can accumulate at points of the domain based upon your geometry. So it sort of motivates some future study in this. You'll notice I didn't present any times in this presentation, and so just because I can restart a simulation doesn't mean that it's time prohibitive. So we need to build a performance model and do experiments to verify what is the compression ratio that is required in order to achieve speed up over traditional checkpoint restart. We can evaluate other methods of selecting compression tolerances. This could be based upon domain, geometry, PD properties. We could use multiple compression tolerances for parts of the state variable for different state variables in order to achieve better compression ratios, in order to achieve less error accumulation, as in the flow that's hitting the cylinder. I would like to thank Blue Waters and for giving me first off the graduate fellowship 2 years ago and continued use of the Blue Waters resources.